This is video number 1 for sections 5.1 and 5.2, Composition of Functions. Let me explain where we're headed in chapter 5. We were doing exponential functions in the last chapter, and occasionally we came across an equation like this. And we couldn't figure out how to solve for x. We couldn't figure out how to get the x out of that exponent position. Well, it turns out that in order to do that, we need a new tool, and that tool is called a logarithm. Chapter 5 is really all about logarithms and how they work and how they're going to help me solve these kinds of equations. Well, it's hard for me to explain what a logarithm is without first covering the idea of an inverse function. And so that's what this particular lesson is all about. The story today begins with what's called composition of functions. And let me see if I can explain that to you using this picture. I have made up two functions, g of x, which is an exponential function, f of x, which is a linear function. I've pictured them as function machines, which we've done before. You know, each one has an in slot and an out slot. And what function composition means is this. Suppose I picked a number and I stuck it into the g of x function, and g of x did its thing and spit me out an output. And then I took that output and immediately stuck it into the in slot of the f of x function. And of course, f of x would do its thing and it would spit me out a final answer. Well, that process where you start with a number and then you run through two functions to get a final answer, that's called composition of function. And there is a way that we write it down, which I've given you here on the handout. This is read f circle g of x. Okay, that's not an O, don't say fog. F circle g of x. You say, what in the world is that trying to say? It simply means f of g of x. In other words, there's a process here. You start with an x, some number. That number gets plugged into the g function, just like we pictured up here. And then that answer suddenly is in the input position of the f function, again, just as we described in the pictures. Let's try this in a couple of examples and see how it works out. So this says find f circle g of 2. Since the circle thing is kind of strange, I would suggest you just immediately switch it over to the other notation. So f circle g of 2 just means f of g of 2. In other words, take 2, stick it into the g function, get an answer, stick that into the f function, see what comes out as a final answer. It's kind of a two-step process, and you can even keep track of it that way if you want to. The first thing I need to calculate is g of 2. Well, I go to the g function. Here it is. I just replace all of the x's with the number 2, and I work out the math. 3 times 4, that would be 12. 12 is not the final answer. 12 is just what came out of the g function. Well, remember, the next step is to take whatever came out here and immediately stick it into the f function. That's what this says as well. The 12 is essentially the value of this red circle. G of 2 came out to be 12, and now I'm sticking 12 into the f function. So f of 12 is what I'm calculating now. Here's the f function. Again, just replace all the x's with 12. And if you work out the math here, that's negative 36 plus 5, which is negative 31. That's the final output, and that then is the final answer to the problem. F circle g of 2 is equal to negative 31. Okay, let's try the second example. Now, if you take a look there, I'm still starting with a 2, but the letters have been reversed on the functions. Now I'm doing g circle f of 2. Of course, one question is, am I going to get the same answer? Is this just the same thing? Well, we'll need to calculate it to find out. Let's switch it to that nicer notation. So g circle f of 2 just means g of f of 2, following our definition we wrote up here. What's different this time? Well, this time, even though I'm still starting with a 2, it's being stuck into the f function first. So I need to calculate f of 2 as a first step. That's the linear function. Replace all the x's with 2. This looks simple enough we can just write it down. Negative 6 plus 5 would be negative 1. That's not my final answer, because then I'm to take the negative 1. Negative 1 is essentially the red circle number this time, and I'm to stick that into the g function. So I'm to do g of negative 1. That was the exponential function, so 3 times 2 to the negative 1. Let's see, how should I work that out? We don't really like negative exponents, so what we generally do is change to positive exponents. There's nothing wrong with the 3, so that would stay up top there, but I would reciprocate the 2 to the bottom, which allows me to change the sign of the exponent, and of course 2 to the 1 is 2, and my final answer there is 3/2. That final answer is also the final answer to the problem. It's the final output, the second output essentially, that is your final answer. Okay? One of the things I think that confuses people when they first learn the notation is, you're used to thinking, well, the letter that comes first when I read from left to right must be the first function used, and it's actually backwards here, if you noticed. It's really whoever's closest to the 2 is the first function used. So 2 goes into the f function first, and then that answer got stuck into the g function. Let's take a look at a second example. This process of composition of functions can also be used when you have tables or when you have graphs. I've got 2 functions here. I have f of x, which is given in table format, and I have g of x. Let's see, that one didn't get labeled. This is g of x here, and that's the one that's given as a graph. And we can do the same sort of thing. So this first example says find g of f of 3, right? That's what g circle f means. G of f of 3. In other words, stick 3 into the f function first, and then take that answer and stick it into the g function. Again, I think the 2-step idea is probably helpful. So the first thing is to find f of 3. F is the table. So I would go to the table. Now, always in a table, the input position is here and the output position is here. So 3 is my input, my x. I just need to find it in the table. Here it is, and clearly it's matched with an output of 2. F of 3 is equal to 2. That's not the final answer, because remember, then I take the 2 and I stick it into the next function. It was an output just a second ago. Now it's an input in the second function. Now the second function is the graph, the g of x function. Of course, on a graph, the x's are always on the horizontal axis and the y's are on the vertical axis, input and output. 2 is an input, it's an x. So I look up 2 here, I go up to the graph. I'm seeing this point right here, which looks to be the point 2, 1. Well, that means when the input is 2, the output is 1. Since that's the final output, it is the final answer to what was asked. We'll try real quickly again. This second one is just going in the opposite direction. Now we're going to use the g function first. So this is f of g of 0. First step, find g of 0. That just means go to the graph. G is the graph. Look up an input of 0. That would be an x of 0. That's just right here. Go to the function. That appears to be the point 0, 3. So in other words, when the input is 0, the output is 3. Then I take the 3 and I stick it into the f function. And we've actually done that already, haven't we? Here's 3 as an input in the f function. The output is 2. Since that's the second output and final output, that becomes the answer to my problem. This process is called composition of functions, and we're mentioning it only because it will help me to explain in the next video what an inverse function is.